Hello, good evening, everyone. Am I audible? Okay, thank you so much. So we will wait for another 1 minute. Maybe others may be joining. In the meantime, I will start recording and I will present my screen. Okay, so recording is being done. I will share my screen. Is my screen visible? Can someone give me confirmation?
Yes, sir, it is visible.
Okay, thank you. Okay. Okay, so what we'll do, we will cover the important concepts of week 5 to week 8. This session is especially kept for the revision towards quiz 2. So, as every week you have been having the sessions, live sessions for all the weeks. So, I will touch upon only on the important concepts considering quiz 2 in mind. Okay, so I shall start with week 5 important concepts. In the week 5, what the course started with the updation of the parameters for sparse parameter, and there we found that if we use vanilla gradient descent, then the sparse parameter gets very few updates. So with that background, we came to ADA grad, so that your sparse parameter also gets somewhere similar kind of updates where the dense parameter is getting. However, in order grade, we realized that for the dense parameter, due to this square root of Vt plus epsilon in the denominator, it starts decaying. So, and for the dense parameter, it was decaying very rapidly. So, to stop its rapid decay, we came to RMS prop algorithm, in which basically the Vt, the increase in Vt, we have restricted by introducing a parameter called beta, and Vt is equal to beta into Vt minus 1 plus 1 minus beta of delta W2 square. So the proportion which we are taking from the current gradient is less, and that's why the decay we have been able to control. However, it will still decay. So the ARDA grad and RMS prop, they both suffer from the rapid decay in the gradient for the dense parameter. Important point to remember that they both are sensitive to this initial eta, because here eta is there. So these both algorithms, they are sensitive to the selection of the learning rate. Now, to overcome the disadvantages of this rapid decay of the gradient for the dense parameter, we came to order delta, where we had adaptive uh, learning rate for both the dense parameter and for the sparse parameter. So here what we introduced that Vt remains the same as the RMS prop. We calculate the gradient with respect to, in the numerator is square root of ut minus 1 plus epsilon, and this ut minus 1 is coming from the previous iteration. We update this gradient and then we update the ut. So ut becomes now beta ut minus 1 plus 1 minus beta gradient wt square. And effectively what is happening, that in the regions where there is a steep descent, Vt is always ahead of ut. Therefore, we get less updates for in the steep region. As we come to gradual or to the region which is not steep, here the Vt starts decreasing and the Ut has got higher value. So here we start having more updates. So this is the adaptive one. Please remember this. And then what we did, we introduced the momentum to this adder delta, like we had done in the momentum gradient descent. So we got like we introduced empty also here. So we are carrying some momentum from back, and then we regularize both VT and MT, and we update the gradient descent W2 minus learning rate divided by root VT plus epsilon into MT hat. This is a regularized one. Now, important point which I had covered during the revision session for this week, that if you don't do regularization, still your the gradient will converge. Only your initial updates, if you have not done, they will be very large. And when you do regulation, you start from here. If you don't do regulation, you start from here. So your initial updates are very large, but still they will converge. Okay. Then from Adam we came to then we introduced NAG and we came to NADAM, and then we came to ADAMAX. In ADAMAX, instead of taking this WT square, what we do, we take maximum of WT or the beta VT minus 1, whichever is the maximum, we take this. And as we are not taking the square, now in the denominator this square root is removed, it becomes VT plus epsilon. RMS max or the max prop, it is the version of RMS prop taking the this concept. So these were the important concepts of week 5. Now in the week 6, the concepts which are covered were overfitting of the model, underfitting of the model. This we know from our machine learning foundation and machine learning practice course. What are the meanings of this overfitting and underfitting? Simple model, bias is high, variance is low. As we increase the complexity of the model, the bias becomes lesser, but variance increases. And the complexity of a model, it is directly proportional to the polynomial degree which we are using. Okay, so to avoid overfitting, what do? We do regulation, and there are various ways of regulation which have been covered in the lecture. The initial ones which we had learned during our machine learning courses were L2 norms and L1 norms. So L2 norm, what we do, we introduce this alpha by 2 W square, and we minimize this whole, the loss plus this extra term. And effectively what happens that we have got, this is the loss surface, and here we introduce this one. And so what in this L2 regulation happens, that it shrinks the weights of the parameters which close to 0, or money, it is shrinking the parameters and it is affecting the parameters which matter. In L1, it brings the parameters, the weights close to 0, and it looks like this. This is the L2 surface, and here it is here. So this is the basic difference between L2 and L1. And other types of regulations were adding noise to input so that the model does not, learn every point. Otherwise, it will do the overfitting. If, for example, we have got data like this, so it will learn every point. So what do? We inject some noise, so to avoid the overfitting of the data. Similarly, we add noise to the output that we have seen. Early stopping, that we don't allow the model to learn all the data points. Okay, so we do, it is a very effective step. The regulation, then data set augmentation we have seen by rotation. Then dropout is a method which we use in deep learning, and it has come basically from the ensemble methods of the machine learning. However, here we cannot do the ensemble method. So what do? In every iteration, we give a probability in the hidden layer that how many neurons will be contributing. So if this is a hidden layer and P is equal to 0.5, so in one iteration, only 2 neurons will participate. Okay, like here, like here. But in the second iteration, if P is equal to 0.5, then maybe this neuron and this neuron will participate. So it is not necessary that in the next iteration, this neuron will not participate, it will participate. And when we come to the output, when we do, we multiply by P for all those neurons. The last one is the parameter sharing and tying. This we use in the encoder and decoder. When you will come to week 12, you will realize this. So these were the important concepts of week 6. Now we come to week 7. Week 7, we started with that. Till now, we have been using sigmoid activation. Now, what are the disadvantages of sigmoid activation? So, sigmoid activation, it suffers from two main disadvantages. First of all, it has got vanishing gradients because we know that sigmoid has got value either 1 or 0. And the derivative of sigmoid is sigmoid into 1 minus x. So in both the cases, when it is 1, it becomes 0. When it is 0, it becomes 0. So in those cases where these values we obtain, so the gradient will not flow back, and that is known as vanishing gradient. Second is it is not zero centered, means all the updates which will take place, either it will take place in the first quadrant or in the third quadrant. There is no update in the second and fourth quadrant. So these were the two disadvantages. Then 10H, there is another activation function. This is zero centered. However, it also suffers from the vanishing gradient, because if we see the derivative of this, so 1 minus tan square x, if this becomes 1, then it becomes 0. So this also suffers from the vanishing gradient. Third is the ReLU. ReLU is ReLU of x is 1 if x is greater than 0, or otherwise it is 0. So you see in the positive side, it will not suffer from the gradient descent. Here it is always positive. However, when you come to the negative surface or the negative values, so it becomes 0. So ReLU also suffers from the gradient descent, this vanishing gradient descent. This I've covered. I will share this document once we finish this session. However, there is a property of ReLU, it converges faster than sigmoid and NH. However, for the negative ones, it still has got a dead neurons, that is gradient descent, vanishing gradient descent. Then we came to leaky ReLU. Leaky ReLU has got a formula x. Leaky ReLU of x is maximum of x or 0.1 of x. So what is happening? Here in the negative also you will get some gradient descent. So leaky ReLU does not have vanishing gradient descent problem. Okay, and the reason is this. From there we came to ALU. ALU also you can see from the graph itself that it also does not suffer from vanishing gradient. Then we came to GALU. GALU is this long equation which can be summarized as x of sigmoid of 1.702 x, and this is the red one, it is the GALU, and it also does not have vanishing gradient descent. No, because here it is not becoming 0. Then we had SELU. SELU also does not have vanishing gradient descent. The main points to remember from week 7 are sigmoid properties, those two properties which you covered, that it suffers from gradient descent, vanishing of gradient descent. Second is it is not zero centered, and if it is not zero centered, what happens? If updates are either in this quadrant or in this quadrant. Second, ReLU is more or less the standard unit for CNNs. In CNNs, generally ReLUs are used. Leaky ReLU, max out, or ALU can also be explored. 10H sigmoids are still used on LSTMs and RNNs. When you will come in next term, or not, sorry, next term in the week 9 and 10, you will be studying RNN, and in RNN, your 10H function is used. And you will come to know what is the reason. GALU is mostly used in the transformer-based architecture like BERT and GPT. So these are the main concepts from week 7. Week 8, the important concepts are convolutions operation, then max pool operation. What is the meaning of that? Very important formula to remember, that output size for both convolution and max pool is floor of input size minus filter size plus 2 into padding divided by stride plus 1. So this is an important formula. Please remember. For example, we are another thing which is takes place. For example, I'll take an example. There is an image, for example, 28 into 28 with 3 channels. And in the question you will be given, you have applied 5 filters of 3 by 3. Find the output size output size, and number of parameters. Okay. So always remember the filter when we apply, the depth of this filter or is always the depth of your input. So this is 3 by 3 by 3. Output size will become, for example, stride is 1, padding is 0. So your 28 minus 3 plus 1 is 26. And number of parameters will become number of filters and the size of filter. 3 into 3 into 3. And if in the question bias is given, then it means that with every filter, there are 5 filters, there is a bias. So you add the number of filters and this becomes the number of parameters. For max pool, there is no parameter. It is parameters are only in the convolution layers and in the last fully connected layer and the output layer. So this will be solving questions on these concepts. So I have already covered the parameters. Now this is a very, very important topic, updation of the filters. How do we update? So till now, everything clear or any doubt in anybody's mind?
May I know how the plus pi comes at last?
Which one?
Plus pi. Last step. That number of parameters. Hello?
Oh, sorry. My mic was off.
It's okay. Okay.
Yeah, yeah. Okay. So I'll cover again. So I'm taking an example that you have got an input 28 into 28 into 3 channels. You are applying 5 filters. The size of the filter is 3 by 3. So it will become 3 by 3 into 3. This convolution filter which is applied, it is applied in 3D. Now when you apply these 5 filters, first filter you apply and you add the bias and you get one output. Okay, the weights are, for example, in this filter, the first filter, your weights are, it is 3 by 3. So I'm taking a simple example. Input is 2 by 2 into 3, and your filter is 1 into 1, and it also takes depth 3. And there is a bias. So when you apply this bias, you will get one output. So if you apply this 1 into 1, so there is only 1. So here you will get same, okay, if you are applying 1 or you apply for example 0.5. So you get one output. So this is one output and here you are adding bias 1. So for the first filter, one bias. For the second filter, second bias. For the third filter, third bias. Fourth filter, fourth bias. Fifth filter, fifth bias. Therefore, your number of parameters are how many? You have applied 5 filters. Size of filter is 3 into 3 into 3. And how many times you applied bias? You applied 5 times.
Fine.
So
Okay.
you got this again, like
Yeah,
this.
got it. Thank you.
Okay.
Yeah.
Yeah. So with these concepts, okay, so let's cover one basic forward prop for this updation of filter before we move to solving the PYPs. So I will request everyone to solve along with me. This is a problem. There is an input 28 into 28 into 3. We are applying 10 filters. size of filter is 3 into 3, stride is 1, padding is 0. We apply these 10 filters, we get convolution layer 1. On this convolution layer 1, we apply max pool by filter size 2 into 2 to obtain C2. This C2 we flatten it and we obtain C3. This C3 which is there, it is connected to a fully connected layer which size is 100 into 1. And this fully connected layer is connected with the output layer which size is 10 into 1, and it is a classification problem for digits. So it is classifying 0, 1, 2, 3 up to 9. That's why it is 10 into 1. Now, what we do for the updation of filter, here I am taking a bias also. So first we calculate the number of parameters. So from input, we apply 10 filters. First we find the size of C1. C1 size is 28 minus 3, padding is 0, stride is 1, so we are not considering them, plus 1, so your C1 size becomes 26 and 26. And your depth size will be what? It will be the number of filters. So there are 10 filters, so your size is 26 into 26 into 10. Is this clear with everyone?
Yes, clear.
Okay.
Also in
Okay.
this,
Yeah. Yeah.
in C1, won't there be 26 cross 26 into 3 because we have the depth of input 3.
Okay. Okay. I've understood your question. So what happens is, okay. So this size which is there, filter size 3 into 3, it takes this depth which is coming from here. So this is like this. This is 28. This is 28. This is 3. This 3 depth, this filter takes. And now it applies is in 3 dimension. And it is applying 10 filters. So first filter, you get this one. Second filter you apply, you get this one. Third filter you apply, you get here. So how many you are getting? You are getting 10. So if you take this now, it becomes 10. Is this clear?
Oh, yes, sir.
Okay. Okay. Now here, for the calculation of parameters, like I covered earlier, so here the parameters will become the filter size. So filter size is 3 into 3 into 3 into number of filters. How many filters? 10 filters. Bias, we have taken that there is a bias, so there will be 10 biases. So your total is 3, 3 is 9, 3 is 27, 270 plus 10 is 280. This is the parameter here. So you can write here 280. Now here we apply a max pool. Max pool size is 2 by 2. Now remember, in max pool, the operation is not 3-dimensional. It is applying on 2D only. So it will apply on this, second, third. So what you will get? You will get the output size and the depth will remain same, 10. Okay. So what is the output size of max pool? So max pool you have applied, and we have considered stride is equal to 2, padding is 1. So input minus filter plus 2p divided by 2, and this is floor. So 26 minus 2 is 24 plus 2, 26, 13 plus 14. So this size is 14 by 14 into 10. Okay. Now here there will not be any parameter because max pool does not have any parameter. Is that clear?
Yes, clear.
Okay. Now you flatten this. Flatten means that this 3 dimension which is there, you just multiply 14 into 14 into 10. So all these values which are there, you are taking in 1 dimension. So it's the C3 dimension will be 1960 into 1. So C3 we have got. Okay. In max pool, there is no bias. Here we have flattened. Now this is connected to 100 into 1 with bias. So how many parameters will be here? 1960 into 100 plus 100. Okay, 1960. So here weights are there, biases are there, normal forward neural network. So number of parameters 1960 into 100 plus 100, 19700. Now this output layer which is there 100, again it is connected to the, sorry, FC1 layer is connected to the output layer. This is 100, this is 10, there is a bias. So now here the parameters will be 100 into 10 plus bias 10 is 110. And this is the total number of parameters. So this how you calculate the total number of parameters. Anyone, any doubt, you can ask me. I can cover it again.
C3 output size alone. One second.
Okay, C3 output. Okay, so what happened? You have got C2. So C2 you got 14 into 10.
Yes, correct.
Okay, so this is C2. And what you are doing, you are flattening this. So here, how many values you will be having? You will be having 14 into 10.
Okay, okay.
So
Linear.
what you do, now you put all these values in one dimension.
Correct, correct. One dimension.
Okay, so it becomes 19602. And
Got
this
it.
is FC1 layer 100 by into 1. This is 10. Here weight is there, bias is there, weight is there, bias is there. So you calculate. Always remember in a CNN, the maximum parameters are in this, the flattened layer and the fully connected layer. And you can see from this example also. Okay.
Yeah, got it.
So,
And all this math won't have a parameters, right?
what, please, can you come again?
In all the cases wherever we see max pool, parameter it won't have any parameters.
Yes, max pool means zero parameter. But you have to consider the max pool to obtain the output size because you have to do the forward pass.
Got it. Yeah.
Okay.
Yes, yes.
So anyone, any doubt till now here? Because on this there will be a lot of questions. You can expect questions of the calculation of parameters. So I can cover again, taking another one example, or we move ahead and we will solve the previous year papers. So in that we will come across a lot of questions. Okay, now we come to, before we moving to PYP, I want to cover basic backprop. Okay, so this one example I have taken. This is the input X. This is the filter. Stride is 1, padding is 0, and you have been given that you find B, which is the convolution of X by K. You apply sigmoid on this B to obtain C. Then you take maximum of this C to obtain D, and your Y hat is sigmoid of D. So this is your forward pass. Actual Y has been given 1. Loss function is given MSE. And your learning rate is given 1. And the question is asking update K and give sum of K. So this basic question we will solve before jumping ahead. So to have understanding clear. Hi Puneet, good evening.
Good evening, Lalitji.
I hope things are clear till now.
Oh, yes, I just joined a few minutes back. So far, wonderful. Thank you.
Okay. So we will solve this question first to get our understanding correct. So what do we do in all these questions? I will suggest always visualize. So do make a diagram. So this is your X, input X, for example. You are applying a filter. What do you get? You get B. On B, you apply a sigmoid, you get C. On C, you take out a max of this, you get D. And on this, you apply sigmoid, you get Y hat. There's another Y which has been given to you 1. So here they will contribute to loss. The question is, we have to update this K. So in CNN, always remember that this filter which is there, when these weights of this filter, initially they are selected randomly. Okay. So in this question, they have given 1, 1, minus 1, 1. So what do we do? There are two steps in this for updation of K. First, we do forward pass. So forward pass, when you will do with the stride is equal to 1, you apply. So this will apply on this. So only these three elements are. So this becomes 3. Then you apply here all 4. Oh, sorry. You apply here. So these 2 are contributing. This becomes 0. Here both are there. So this becomes 2. Now here all 3 are contributing. So this becomes 2. Here 2 are contributing 0, and here only 1 is contributing. This is 1. I hope this is clear. Okay? This is. Now you applied sigmoid on this. So 3 sigmoid, for example, we take. Can somebody give me 3? If I'm not wrong, it is close to 0.95. 0 is 0.5. 2 is 0.88. 2 is 0.88. And 0 is again 0.5. Any mistake here? 1 and 1. This is also 1 because these are the 3. So this is the convolution. Here we get this is 7.3, and here we get 7.3. Now when we move from this C to D, we are taking the maximum. For example, only 0.95. Or in the question, yes, 0.95. We get sigma of this, so we get some value, for example, 0.95. I will just find 0.95.
Oh, 0.95.
Huh?
0.95.
0.95 sigmoid.
Yeah, it's okay. Segment of 0.95.
Okay, it's 0.27 or 0.278. Oh, sorry, I've not done the minus. It's 0.72. Okay. Have you understood this forward pass again? We have applied the convolution, we got sigmoid of this, we got C, then from C we got the maximum, which is 0.95. We applied sigmoid on this to get the y hat, and y hat came at 0.27. Okay.
Actually, in this, will the steps will be given by them in the question paper, or we
yes. Every step will be given, including bias and including everything.
Okay.
And please pay attention towards the bias here.
If bias is given, then where we should add?
Yeah, yes, I will cover in the PYPs, or we can, if for example, bias is given 1 here. So what will happen? Everything will change to 4, 1, 3, 2, 1, 2. Understood?
Okay.
Okay.
Got it.
So presently we will do without bias, and later we will do with the bias also.
Yeah, sure.
So forward pass we have done. We have got these values like what we used to do in the artificial neural network. These values we will be using in the backprop. Now objective is, so step 1 is forward prop, step 2 is backprop. So for backprop, objective is what? Objective is to update K. For doing that, we need del L by del K. So apply the chain rule, del L by del K is equal to del L by del y hat, del y hat by D, del D by del C, del C by del D, and del D by del K. Is this clear? Now,
yeah.
So this is an MSE. So del L by del y hat straight away becomes y hat minus y. Okay. This is a sigmoid. So here this will become y hat 1 minus y. So we have come here. So this was the output layer, and we have come here, and we have got the loss here. Now see, the C which is there, max is 0.95. When we do the back propagation of loss, we have got some loss gradient here. Now this loss, as this is max, so this loss will come only from where? It will come only from 0.95. Rest everywhere, no neurons here. These neurons are not participating.
No.
Yeah. Okay. And this 0.95 from, so delta D by delta C, if you think, it will become 0.95, 0, 0, 0, 0, 0. Is this okay? I can write it like this. Delta D by delta
Yes.
C.
Yes.
Yeah.
Now, when delta C by delta B, C is a sigmoid, so delta C by delta B is the sigmoid into sigmoid. Is this okay?
Yeah.
Okay. Now, when I multiply this, so this will become 0.95 into 0.95 minus 1 minus 0.95. Into 1 minus 0.9, and this is it. And this is the delta B by delta K. Is this clear? Now you calculate this one, and then you multiply by here. So you get to know that only your this neuron has been participating, and how much it is participating by this value. So you multiply 0.27 into minus 1, y hat 0.27, 1 minus 0.7, 0.73 into 0.95 into 1 minus 0.95, and rest all neurons are contributing 0. And you have to operate with this on delta B by delta K. So this value, whatever you get, for example, just I'm taking a fixed example, this will be negative. So just take, for example, it is 0.10, and this is 0, 0, 0, 0, 0. Now B is convolution of A by K or X by K input. Now for stride is equal to 1, to get delta L by delta K, this delta B by delta K, which is X, you do the convolution of X by this, and you will get delta L by delta K. Is this step clear? Any doubt in anybody's mind till now? Suraj?
If possible, could you finish the problem so that?
Okay. So what we will do, we will be doing similar questions of the PYPs. So
Okay.
this set will become much more clearer.
Okay.
Just remember that in this CNN, what you do, for example, I will make the diagram. This is X. You apply a filter, you get some output. On this, you do some activation function. It can be ReLU, okay, it can be sigmoid, it can be anything. You come here on this, again you do some activation function, or you get an output. For example, here you do max, so you will get a number. You apply a sigmoid on this to get y. So
Okay.
make a forward pass. Making a forward pass is easy, and jot down those values which you are getting here. Okay, so this becomes your B, C, D. Okay, and this is y. You will be given y. You will also be given either you will be given loss function, or in many questions in the PYPs you have been given del L by del y, right, straight away. So you don't have to worry. Now in the back prop, there are three distinct parts in the CNN. One is till output layer, and one is till this convolution layer. So this straight away here you have to find chain rule. Del L by del D is equal to del L by del Y into del Y by del D. So depending on the activation function, you will get a value here. Okay, and generally in all the PYPs, this is a scalar value. because sigmoid has been used. So this is the value, this is the loss gradient now which will flow back. Now this was a maximum. So here, if it is a max, for example, I'm just taking one example of max. It might be different activation functions. If it is a max, then from wherever this value is coming, the loss will flow only from that neuron. Rest all other neurons, they become zero. And as this is sigmoid, so derivative of a sigmoid is sigmoid into 1 minus sigmoid. So now this neuron which is there, rest all became zero. You apply this sigmoid into 1 minus sigmoid to get this. This is the second part. So one part is here, you bring the loss gradient here, calculate. Now calculate the loss gradient, bring it till now here. Now when you get this value, to get now delta L by delta K, this will become this input which is there X and convolution by this delta P L by delta P. Is this clear? These steps. In all
Yes,
your
sir.
activities, there nowhere stride 2 has been used, only stride 1 has been used, and this is the straightaway for stride 1. Okay, many of you might be having doubt that delta C by delta B will be having large size. I'm just covering the shortcut how to solve this question. Okay, from the quiz point of view. Okay, now if these concepts are clear, I will just take 2 minutes of break. I'll have a glass of water and then I will join back and we will start solving PYTs. Is that okay?
Yes, sure. Yes.
Yeah. Okay, I'm back. So we will start solving PYTs. Am I audible?
Sir, I
Yes,
had a
yes.
question. If you can go
Yeah.
back to that.
Yes.
So I just wanted to confirm one thing. So in one of the previous sessions, I don't remember which,
Yeah.
the gradient of one of these ReLU and or max, we had taken one instead of two. So like here,
Okay.
we know that the max value is two.
Yeah.
So instead of two going back, we had taken one there because all the loss was flowing through that.
Yeah.
So I just wanted to confirm that whether we'll take 0, 2, 0,
No,
0 or
you're right. I'll give you an example of that scenario. What happens? For example, this is your input. You apply a filter. You got something. You applied, okay, for example, ReLU, and then you got something. you applied max, you got something, and you applied a sigmoid, you got 500. Okay. So in this question, you see in from here to here, there is no sigmoid, only ReLU and max is there. And for example, I'm just taking one example that here we came -1, 2, 1, 1. This was your value. So what ReLU did, it made again 0, it made 2, it made 1, it made 1, and max we got 2. Is that okay? Is this looking familiar?
Yes, sir.
Okay. So now when you do the back prop here, so what I'm interested first, I want to find the loss gradient here. So I find here. I get some value, for example, B, C, D. Now this 2 which is coming, it is coming from this neuron. So I keep this 2 only. Is it okay? And rest everything becomes 0. Rest becomes 0. Is that okay?
Yes, sir.
Okay. Now this becomes 0, this becomes 0, this becomes 0, this becomes 0. Now when you take the derivative of a ReLU, remember derivative of a ReLU is either 1 or 0. Okay. So this will become now 1.
Okay, so for max, 2 will remain, and
Yeah.
for ReLU, we'll take 1 or 0.
Yes, yes.
Okay.
Derivative of a ReLU, for example, if y is equal to ReLU of x, then dy by dx is equal to 1. If x is greater than 0, it can be anything, it can be 100 also, but derivative will be 1, or it is 0 if it is less than 0. Okay, this is the concept which has been used.
Got it.
Okay, thank you. So, shall we move ahead and jump into the lake to have a quick?
Yes, yes, sure.
So I will. So these are the. I have compiled like a week wise all your questions PYPs. So this is the question: what are the possible outcomes if we don't do bias correction and add-on? So this I covered in the revision session also. It will lead to initial updates which are much larger. Okay, here will be larger, but still it will converge. Is that clear? Okay,
Yes,
and
clear.
I have given in the this also. Now consider the assertion and the corresponding reason. The RMS prop algorithm starts oscillating around the minima. And second statement, it is sensitive to initial learning rate value. So what is the, anybody can throw light on this or any understanding issue here? That A is true, but here this oscillation which is happening, it is not, it is, this statement is true, that it is sensitive. But this oscillation, is it happening due to this? Or it is happening due to some other reason?
It's happening due to the gradient difference.
Yes, yes. It is happening because in RMS prop, your VT which is there, it is beta into VT minus 1 plus 1 minus beta into delta WT square. So it means this, and your WT plus 1 is equal to WT minus nu over root VT plus epsilon into WT. Now, this value which is there, VT, you were carrying some value VT. Now, depending on this WT square, this value which is there, either VT can increase, it can decrease, or it can remain 0 if you're, same if W2 is 0. So this value is there, which is there, either it is increasing or decreasing or remaining constant, due to which your oscillation is happening around the minimum. It is not happening due to the initial learning rate value. Okay. In the lecture, it has been given, and there might be misunderstanding in your mind. Lecture covers that if you select appropriate initial learning rate, then this oscillation will not take place. But here, this question and a reason, they both are different. It is asking that is this oscillation is happening due to this? No, it is not happening due to this. It is happening because your this VT which is there, or effective learning rate which is there, it might decrease, it might increase, or it might remain same. That is the reason. Okay, is that clear? And anyone, any doubt?
No doubt.
So one question is there.
Yeah.
Is it is sensitive to initial learning rate? So the learning rate is, it means the learning rate is decreasing the oscillation value, right? Right. So
Uh,
actually it's not oscillating because of initial learning rate, but actually it's decreasing the value of oscillation during the learning curves.
yes, yes, that might be true. Yeah, but this for the oscillation, this learning rate okay, which is there, it is not the reason. Remember this. Okay. RMS prop can start oscillating around the minima, but this behavior is typically due to the factors such as the learning rate and the decay rate of the moving average. This is the important. This is the due to the decay rate. While RMS prop is sensitive to the initial learning rate, the reason for the oscillation is not solely due to this sensitivity. It can be influenced by the decay rate and how the learning rate is adjusted over time. This is the reason. Okay. Okay, so these two questions are covered. Now, what are the possible outcomes if we don't do the bias correction in Adam? This is the same question. Which of the following statements are true with the order delta? In a surface with steep curvature, both Vt and Ut decrease. No, they increase. So this is incorrect. At low curvature regions, Vt starts decreasing and the learning rate starts increasing. This is true. I covered here that this is a steep region. This is the low curvature region. So here Vt will start decreasing, and due to which this numerator part which is there Ut minus 1 plus epsilon and Vt minus 1 epsilon. So your numerator is higher than this. That's why your learning rate will start increasing. This is the reason. Order delta allows numerator to increase or decrease based on the current gradients only, not based on the current gradients, because these Vt and Ut, they are taking the values from the past gradients. Adder delta converges quicker than RMS prop? Yes. So for this, I will give you a hint. Adder grad converges faster than vanilla VGD. Adder grad RMS prop converges faster than adder grad, and adder delta converges faster than RMS prop. So this you can remember. Okay, I've covered it here. So this is there. Okay, the statement that the bias correction in Adam optimizer is an absolute requirement for it to converge to local minima, this is false. Okay, so if this is the points, and if we don't do the regulation, if with the regulation, your gradient will be somewhere like this, it will converge, and without regulation, your updates will be like this, and still it will converge. Okay. Which of the following optimization algorithm adapts the learning rate based on the current gradient and the history of gradients? So somebody can give me? So adder grad is there, RMS prop is there, adder delta is there, all which we covered in the week 5, all are on the current gradient and the history of gradient. So which one is not there? Gradient descent with exponentially decaying rate, learning rate, no, it is with the same RMS prop, Adam and adder delta. Natch, no, we don't do with the step decay. Now we come to this question. Assume that we are updating the weight and bias of a neuron using adder grad optimization. This is the adder grad optimization, where n naught is the initial learning rate and v minus 1 is 0. The plot below shows the change in learning rate over iteration. The blue curve represents the change in learning rate for weight and the red curve for the bias. So this is for red is for bias and this is for weight. And what they're asking in the question, the statement that the gradient of the weight W changes slowly as compared to the gradient of bias if we move on the contours of the loss surface is true or false. So this is true. Why? Because here the bias from here also you can make out, first of all, it has decayed. Second, you can make out that bias is the dense parameter. And for dense parameter, we knew that your learning rate here, it decays faster than for the sparse parameter. Okay, that is the reason. The statement that the gradient of the bias changes rapidly as compared to the gradient of weight W if we move on the contours of the loss is true. The same reason. The algorithm converges to the local minima after 500 iterations. You can see here that it converges somewhere here. Both became less than 500. Okay, so that is also true. Suppose that a neural network has millions of parameters, weights and biases. A team decides to use an optimization algorithm with a learning rate scheme that is local to each individual parameters in the network. Moreover, the learning rate changes in each iteration based on the magnitude of gradients pertaining to a parameter in the past. Which of the following optimization algorithms satisfy the team requirement? So what it is saying that we have a W0, W1, W2, many are there, millions. But for everyone, we are changing the learning rate. So this happens in all the adaptive gradient descent algorithms. So it will happen vanilla GD for the exponential decaying. It will not happen for the ADA-grad, ADAM, NADAM, RMS prop. SGD will then such it will not. Suppose a data set has n samples and each sample has two features, f1 0 or 1 and f2 0 or 1. Assume f1 is a sparse feature and f2 is a dense feature. Further, we apply stochastic gradient descent on this data and plot a contour plot of the loss surface and observe the movement of parameters trajectory. W1 and W2 with the parameters to f1 and f2 respectively. Assume bias to be 0. Parameters are initialized to 0. Contour plot of loss surface. What is the initial movement expected to look like if W1 is plotted on the horizontal and W2 is plotted on the vertical? So see, for the SGD, we saw they have given this is F1, this is F2, W1, W2. So your initial updates, and it is a SGD. So it means your gradient update is taking place for every point. So if all the points are in the same range, so it will take the updates for what? It will take updates for the dense parameter first. And if the points are displaced every other point, then it can be zigzag also. So that's why these two answers are correct. Either the zigzag movement along the vertical or mostly straight along the vertical axis, depending on the data points. A model has n of parameters, weights, and biases. Suppose that each parameter takes b units of memory for storage. Moreover, we need additional memory to store the gradients of the parameters to make a parameter update during training. Assume mini batch gradient descent is used for training. Choose the correct statement. So here they have asked regarding the memory. So Adam takes more memory than ADA-grad. Can somebody tell me why? Due to beta 1 and beta 2. We have got both beta 1 and beta 2, due to which we are storing both VT also and MT also. So due to this extra MT, it will have more memory requirement than ADA-grad. ADA-grad takes more memory than RMS prop? No, because in ADA-grad there is no beta, whereas in RMS prop there is a beta. So you will need some memory for that beta. Vanilla GD takes lesser memory than ADA-grad, yes, because in ADA-grad we are storing VT also, whereas in vanilla GD there is no VT. Therefore, these are the correct answers. Which of the following optimization algorithms encounter problem of oscillating around the minima? So this we have seen, RMS prop we have seen, NAG, it takes correction before, however, it also oscillates. Adam has got a momentum, that's why it also suffers from the oscillating around the momentum. And momentum based gradient descent we had seen in week 4 that it also oscillates. Now, next question, we know that if the weight update rule for the gradient descent is given by this, and equivalently we can write this. So these are the statements. Wt plus 1 minus W0 is greater than or equal to Nt into T into max of Wi. Nt is a constant learning rate. Or Wt minus 1 W0 is less. Or if it is exponential, it will be less or in the case of constant learning rate, it would be greater than equal to the minimum of the delta wi. So what you can do, how I solved, what I did, I took constant learning rate, I took 5 values of gradient descent, different, and I calculated at every step, and I found statement 2 and 4 correct. And then I did with the exponential one. So exponential decaying, I just took random n1 1 and 2 0.1 0.01, and with that, when I calculated, I found this statement is also correct, exponential, and this I found incorrect. This is the way how to solve it. Next question is, this is a data set where X are samples features. The first column is for bias, so this is X0. The notation X0 denotes jth feature of this. Suppose we pass each of these samples to sigmoid neuron. Suppose we initialize all the parameters values to 0.1 and use the loss function MSE. Further, weights are updated using a stochastic gradient descent algorithm for 5 iterations. Which of the following weights will get updated at least thrice with non-zero gradient? So from week 5 concept, we came to know that for a parameter to get 3 updates, at least there should be 3 values. So X0, W0 will get update. It has got more than 3. It has got 3. This will all get update. This will not get updates. This will get updates. This will get updates, and this will not get updates. So this is straight away from the concept of week 5. Come to consider a function fw is equal to w plus 1 square. Suppose we want to find the value of w for which the function attains its minimum using iterative algorithms, namely gradient descent and AdaGrad. The update rule for the AdaGrad algorithm given: assume n is 0.5, v minus 1, 0, w is equal to 0. Select the correct statement from the following statements. So it is again straight away concept. You don't have to do any calculation. AdaGrad takes lesser number of iterations than vanilla gradient descent to converge. Will it happen in this case? AdaGrad, why do we use? We use AdaGrad only for the sparse parameter. Here, it is not sparse. Okay. And what will happen if it is not sparse? Then AdaGrad decaying, that dense parameter is there. Its learning rate will decay and it will take more number of iterations to converge. Okay, so that's why this second statement is correct. We use adaptive algorithms only in the case of sparse parameters. Which of the following statement is true about adaptive gradient descent algorithms? They are more suitable for sparse data covered just now. This is incorrect. They add additional computational complexity to the vanilla gradient descent because due to the VT, beta, and all that. Anyone, any doubt you can tell now here in any concept? Hello, Suraj. Hello.
Hello.
Hello. Am I audible?
Am I audible? Yeah. Good.
Hello, Puneet. Am I audible?
Yes, sir, you're audible.
Okay. Okay. So
yes, sir.
Hello?
Yes.
okay. Okay. So till now, any problem in any question till now here? All are conceptual questions.
Yeah, the previous question was quite interesting though, like how you identify that it's not sparse.
Yeah, because they have given.
Right.
Yeah, they have. Okay. They have given.
Right.
Okay. Now we come to this again. Okay. So here is the question: the effective learning rate in RMS prop may increase or decrease, and this is due to the exponential averaging of the squared gradients. So this we covered in earlier question. That yes, this is the reason due to which this increases or decreases. So this is true and R is the correct reason. Okay, already we have discussed this question. Now we come to this. Suppose we modify the update equation of Adam. That this is Adam and beta 1, beta 2 is between 0 and 1. Epsilon is a very small number, greater than 0. Suppose that vanilla unmodified Adam algorithm converges while training a model, then the statement that using the modified algorithm will not converge due to missing bias correction. This already we have covered, that it will converge only the initial updates will be large. Okay, so this is false. Okay, now this is about a diagram. This is a simple diagram. Here they have given y hat is equal to w1 plus x1. This is a mean square error. M is the number. Assume both are this. So from here we have to make out which one is dense and which one is sparse. So we have to just identify where the updates are taking place. So updates are taking place in which direction? In W2 direction. In W1 direction, very less. So W2 is for x2. So x2 is sorry. Okay, this direction. So this is the direction for W1. W1 is taking updates, so x1 is dense. W2 less updates, x2 is sparse. Okay, so that is the understanding of this. So update rule for the Adam. This is the Adam standard, and what they have written that if you modify the equation for the momentum, yeah.
So in the last question, how did you figure out the direction?
Okay, direction you see from here from the diagram, the loss surface has been given. So this is the one, the distances between the lines. What does it tell you? The updates? On a contour, that this distance between the lines which is there, the loss surface, it tells you the updates which are taking place. So your updates are taking place in which direction? In W1 direction.
Right.
Okay. So it means this W1 parameter which is there, X1, it is dense. Okay. Here you see the distance is higher. So very less updates.
So had it been in the W2 direction, then what would have been the case?
Then the diagram contour would have looked like this.
Okay. Got it, sir.
Okay.
Got it, sir. Thank you.
Okay. Here what they have given that instead of this empty which is there, if we modify empty as per this, we introduce one more this, then what will be the bias corrected version of empty? So remember in the lecture, what the professor had done, he had arrived at the empty hat. Okay. In this document, I have done the same, but due to the paucity of time, I will not be able to explain all these steps. Okay. I have followed the same steps which professor has done. That I have done M0. If we take this formula, for example, what they have given for the empty, then I have calculated M0, then I have done M1, then M2, and from here I have come to that M at T. So I have reached here that MT, how it will look like. And this gradient of WT comes out expected. And this term which is there using the knowledge of class 12 mathematics, I have expanded and I got the answer which is MT hat is equal to beta T plus 1 into MT beta T plus 1 minus alpha T plus 1. So it is a slightly lengthier this. I don't expect from all of you to do this during quiz. So just take a, I will say, इसको रट्टा मार के इसको बस रट्टा कर लो कि ये वाला भाई ये वाला आंसर है, ठीक है? Is that okay with everyone? If someone wants, okay, I can take a session to explain all the steps, but I'll share this document for understanding of it. That's okay, Puneet?
Yes. I like your advice, Ratta Marlo. Okay.
So now, which of the following optimization algorithm changes the learning rate on for each iteration and epoch? For each iteration, we are changing the learning rate. So for RMS prop, the learning rate might not change if your this is not changing. Vt plus eta, then it might not change for each iteration and epoch. Similarly for NADM also, oh sorry, this RMS prop it will change, NADM it will change, NAG will change, and GD will change. But if you take my understanding, then for each iteration it is not mandatory for RMS prop, because like I covered earlier, this Vt plus eta, if your delta W square is 0 for a particular point, but it is for a point. Here they are covered for an iteration, so we consider that they are taking all the.
Excuse me, sir.
Yes.
So could you please adjust your mic? Your voice started breaking when you started discussing the question.
Okay.
I think some background noise also started.
Yeah.
Actually, fighters are flying.
Right. Next to the.
So give me just 30 seconds. I will explain this again. Okay. Now is it clear now?
Voice is coming, sir.
Okay. I'm not speaking, but better take off. Okay. Am I clear now?
Better.
Yeah. Okay. So the question is, which of the following optimization algorithms change the learning rate eta for each iteration of an epoch? RMS prop we have seen. I am saying it is an iteration. If what happens if somebody asks you that will the learning rate will change for with every data point? For example, if you're doing stochastically and you are using RMS prop, will it change with every data point mandatorily? It will not change, because this is Vt plus eta, and your Vt is coming from beta into Vt minus 1 plus 1 minus beta gradient Wt square. So for some data point, if this gradient is 0, so it will not change. So I'm just covering that this question, if it is asked in a different format. For this particular concept or context, it will change for all the algorithms.
Does Nesterov also change learning rate?
Here they
NAG?
with the cyclic learning.
What is that? Okay, cyclic learning.
You start with one rate, you reach 0, again you come here, again you do, okay. So that's
So NAG also works with, so this one is trying out different.
Yes. And gradient is a normal with the exponential wave decay rate, it will also change.
Okay.
Now, so week 5 all questions are covered. Now we come to week 6 concept. Suppose you have a deep neural network trained on a data set with a small amount of labeled example. After applying L2 regulation during training with a fixed value of regulation parameter, the following observations are made. The empirical error decreases significantly. It means your training error is decreasing. The true error remains high. It means your test error remains high. The variance of the error on different subsets of the training data is relatively low. So variance where it is low, when it is overfitting. Yeah, when the training error is very less and it is overfitting. So from all this, it comes out very clearly. This is a case of overfitting. Okay. So that's why this option is the correct one. The model is still overfitting, and we have to apply more regulation. And how to apply more regulation? This alpha by 2 W square value is there. Now tune this hyperparameter alpha. This one.
Sir, can you repeat what you just said about alpha?
Just give me 30 seconds. This matrix is more. In the question they have given that already you have done the regulation. So you have applied some alpha. So already this has been done, but still it is overfitting. So what you will do? Tune alpha. Okay.
Okay, sir. Okay, sir. Got it.
Okay. Now, after training a neural network using VGD, you notice it performs exceptionally well on the training set, but poorly on the test set. So again, what it is, the case of overfitting. And how do you solve the overfitting? By using the regulation methods. In all these methods, these are the only one for the regulation. These are the optimizers. Optimizers are for the different reasons. Now, this is a question. Team A constructs a data set X and Y that contains n samples. Each sample belongs to R, uniformly sampled from the function. This is a function, and 1 plus C1x up to x1p in the interval -1 less than equal to x with p less than 80. So this p is there, which is there less than 80. The data set is then given to team B with the information that samples were not corrupted by noise. So there is no noise. They split the data set into training and a test validation set. Team B assumes a polynomial function gx up to x of d of unknown degree. They decide to vary the degree of the polynomial from 1 to 100. For instance, setting d is equal to 2 gives this parameters are estimated. They measure the mean squared error for each setting. Select the two statements. So, the statement 1, the training error becomes 0. Is there any d for which training error will become 0? Yes. In the question, just try to understand the question. There is a function 1 plus c1x plus c2x square plus c2xp. And this p which is there, this p is less than 80. These points have been taken and there is no noise in this. Now these data points, they have been given to team B. Team B, what they will do, they start estimating with the another function with k0 plus k1x plus k2x square plus up to k2xd x of d, and d is 1 and 100. So they have asked that is there any d for which your training error will become 0? So for d, if we select d is equal to p, whatever the p was there, it will become 0 because there is no noise, and that will actually beat all the data points. Is this clear? Okay, any doubt in this explanation with anyone? Suraj? Yeah. Okay. Now, second, the testing error becomes 0. Why test error becomes 0? Because we have, this was a function, there was a p, and we have selected d is equal to p. So then we can fit all the data points because there is no noise. So test error also becomes 0. Both the bias and variance of the model become 0. Yes, for the d is equal to 80, no bias, perfectly fit. Model has 0 bias and non-zero variance. Is there any d? Yes. If d is greater than p or 80, then it means it has become, the complexity has increased and the bias will become 0, but it will have non-zero variance. Model has non-zero bias and non-zero variance. Yes, if your degree is less than p is equal to 80, then it will not fit the data points. So it will be something like this. Okay. So that's the understanding straight away from the concept. In general, applying regulation to an overfitted deep learning model, what happens? So if we apply regulation to an overfitted, so your training error decreases, increases, your test error decreases. So these are the two. It increases the training error, it reduces the testing error, and it improves the generalization ability of the over parameterized model. Again, from regulation, assume a team has trained a CNN model for image classification. They observed the model was performing poorly. That is, both training and testing errors were high. This is a case of what? When both training error and test error are high, it is a case of underfitting. So what do? You increase the, what should be the more appropriate measure that might improve the performance of the model. So what do? You increase the model complexity. Okay. So questions are straight away from concepts. So no need to do calculations and all that. Similarly, suppose that we sample 100 data points from a uniform distribution. For each data point, we compute y is equal to fx, where fx is some real valued function. Then we build a prediction model f dash x. The mean square error is given by this. So here again, they have said here that there is no noise. So we have to select the correct ones. E of fx minus fx square. These are the ones I have explained. This is from the straight away from the lecture. Error is equal to e is equal to y. This is the predicted one, f dash x. Or I can write this also, fx, y is nothing but fx minus fx square. E of f dash x is fx in this case. E of e, there is no noise, so y becomes fx. And f dash x can be fx. And then in that case, will not be any bias and there will not be any variance. Okay, this is a question. Target variable is equal to fx plus somebody can read epsilon. Okay, so this is here. There is a noise which is related to xi. This is a random variable noise distributed normally. About 1000 points are sampled from true function fx to form a training set. Suppose that the prediction of f dash x is sufficiently complex so that fx belongs to f and of x, then the statement that training error is lower bound by sigma square, that is a variance of noise, is true or false. So this is false, and the reason is we know training error is equal to empirical error plus the variance of noise. Therefore, and this noise which is there, variance of the noise, it cannot be removed. So training error becomes this variance plus some value. So in case empirical error is also becomes 0, then also your training error will become, at least it will have the variance of the noise. So this is the lower bound.
So sir, in this case, isn't the answer true because we're getting training error as lower bounded by
Sigma square.
Oh, sorry, sigma square.
Yeah. Now a data set contains 15 data points and fx where x belongs to r. Data points are randomly shuffled, split into train and test. Training set contains 10 data points. So there were 15, 10 have been taken for training. Two models, A and B. A has got a polynomial degree of 5. This is A. This is B, which has got a polynomial degree of B. The diagram shows there. So the questions are, model A has a low bias and low variance. So see, model A complexity is 5. So as complexity increases, your bias, what happens? It is decreases, your variance starts increasing. So it will not have a low variance. Model B has a low bias in comparison to model A. So here you have to read these statements in comparison to model A. So model B complexity is 7. So therefore its bias will be lesser than model A. However, it will have a higher variance than model A. So that's why these two statements are correct. Okay, slightly these options are ambiguous. They should have clearly written that model B has a lower bias than model A. Then it becomes clear.
Okay, right.
Yeah, otherwise it gives a different meaning altogether. Okay. A team trains a deep learning model for regression problem using mini batch for 10 epochs. In all the epochs, the training error remained high. High means at the constant k belongs to this. Validation error remained at constant this. So if the training error is high, it means what? Yeah, it is a underfitting. And when does underfitting happens? When it is a simple model. And what is the properties of simple model? Simple model has got a high bias and low variance. Okay, so from
simple model should have low bias.
No, it has got a high bias.
High bias.
Yeah.
Okay.
So how does it have high? I'll just cover. For example, your data points, they were like this. Okay, and when you make a simple model, so simple model will predict like this. Okay, so these bias values which are there, they are there. Okay. However, when you have more and more, so your variance which is there, variance will be less. Okay.
Hmm.
So this variance which is
underfitting, but the underfitting means high bias and high variance. Right?
Underfitting, see what I said here, they have not given underfitting. Here they have just said that training error remained high. So training error, if it is high, it means okay, this is a case of this model where the data points, they were here. Okay. So this model will have high bias and low variance. So what you have to do, you have to increase the degree of your model. So that okay, if you increase the degree to 3 or 2, so it will start okay, like this. So your bias will decrease, but your variance will increase. Okay. Now this is a question. Okay, this is an interesting question. All weights and biases except B1 are initialized to 1 and B1 is initialized to 10. Suppose that input is all ones and the true label y is equal to 1. Model using this is the regulation method. Model parameters updated using SGD with eta is equal to 1. Update the parameters by running the model for one iteration and enter the sum of updated parameters. So basically this question has been asked to check your understanding about this regulation, L2 regulation. So we have to do some mathematics on this. So what do we do? These are 3 inputs to this and there is a bias. So we calculate A1 comes W express B is equal to 30. We pass it through ReLU. Here ReLU also gives 30. Now y hat is equal to 10 H of this 30, which comes 0. And here, if you see in this, again, they have given alpha is equal to 1. This hyperparameter which is there, it is 1. So now this is your loss. For loss for the regulation L2 method, we write L theta is equal to half y minus y hat square plus half theta square, straight away from the formula they have given. So for W3, we have to update. So del L by del W3 will become y hat minus y because it is a mean square error, and then del y hat at del W3. So using the concept of backprop, y hat minus, and here when we do derivation of this W3 regulation term, it becomes W3. So this will become y hat minus y del y hat by del A2 here, del A2 by del W3, and this is W3. Now for the 10, okay, we know 10 derivative is 1 minus 10 square, and W del A2 by del A3 is H1, and here it becomes W3. So when you solve this, So you will get del L by del W3 as 1. And your W3 initially was 1. And eta is 1. So your new W3 becomes 0. Similarly, for W1, which is W0, W1, W2, you apply the chain rule, get this regulation term here. When you do the derivative of that, so again your these terms will come, which already we have calculated. Y hat minus y, derivative of tan, here will come W3, here 1, and this is your input, plus W1. And when you do this, so here you will get 1 minus this becomes 0. So this becomes W1, this term, regulation term. And your update will be W1 is equal to W1 minus this. So your W1 and W3 all become 0. And why it is happening? It is happening due to only one reason, due to this tan square. This is making that 0. Do this calculation, it is a straightaway calculation. No complexity in this, and you will get the answer. Next question is the diagram below shows contours of a loss function L theta hat theta is equal to L theta plus alpha into sigma of theta. So we know in this represents L theta, and this is the one which is coming from L2. This is alpha sigma of theta, and where they meet. Suppose we use L2 regulation, then choose the correct statement from the following statements. This is the correct statement. So he's saying the dotted circles represent contours of regulation term that we have explained. The solid circles represent the L theta that I've explained. This alpha hyperparameter which is there, it is between 0 and infinity. This is correct. The L2 regulation is independent of the input samples used to train the network. So remember this concept that this L2 which we are using, this is the regulation for L2. This term which is there, it does not depend on the input. It is depending only on the weights. Now somebody can think that weights are coming from the input. Okay, that understanding is correct. However, when you consider this, you are minimizing this whole term. So this regulation which is there, this one, it does not depend on the input. What it does, it is just trying to, this loss which is there, L theta, it is bringing down to close to this surface. So it is shrinking the weights, and it does not depend on the input. This you please remember. I have given the explanation also here. So here, what are the maximum and minimum possible values of derivative of sigmoid? I think there was a question in GA, so it is straight away sigmoid max. Sigmoid is always between 1 and 0. Derivative is sigmoid of x into 1 minus sigmoid of x. You can do that, and the derivative max will become 0.5 into 0.5, which is 0.25, and minimum when it becomes 1 and 0, then sigma of x, 1 minus sigma of x becomes 0. So it is between 0 and 0.25. And this is precisely the reason that when the loss gradient flows through a sigmoid neuron, if a loss is coming, flowing through a sigmoid neuron, always the loss gradient shrinks. The loss might have been, for example, if I give you an example, it might have been 5, but when it will flow through this, there is a sigmoid, it will shrink. That's it. Consider a feed-forward neural network containing 3 inputs, 1 output.
So you weren't audible. Can you please explain the last concept again?
Okay. So last concept was that whenever the loss flows through a sigmoid neuron, it always shrinks. Take an example, sigmoid, loss is coming. So here what do? We do sigmoid and 1 minus sigmoid when we take the derivative. So when the loss is flowing back, it always shrinks. Whereas if you flow through a ReLU, at least the value which goes back, it is 1. Here it gets multiplied maximum loss into 0.25. Is that clear?
Yes, I got it.
Okay, this max value which is there, it is 0.25.
Okay.
So here the loss value which will come, maximum will be loss into 0.25. In the case of ReLU, it multiplies by 1. Okay, so just for the concept I wanted to cover this. Consider a feed-forward neural network containing 3 inputs, 1 output, 50 hidden layers containing 2 neurons. Activation function is all ReLU. Output layer uses the sigmoid activation for binary classification, trained with a binary cross entropy loss. Assume all weights are initialized to 1, biases to 0. For an input this, what will be the output of the neural network? So it might look complex, but you just solve. So A1 is equal to W101. Your first input is there, which is, so you get 111 and the values are given -10, 5, -20. So you will get -10, 5, -20. And when you multiply by this, you get -35, -35. When you apply ReLU on that, both becomes 0. And this is a case of a dead neuron. So when it becomes 0, now when you do forward pass, everything starts becoming 0, 0, 0. So your A51 is also there, which becomes 0, 0, because here you got 0, 0. So now at the output, you will get the output is what? Sigmoid activation. So y hat will become sigmoid of 0, which becomes 0.5. So this is the output. So they have given just to check the concept, how to do the forward pass. Okay, this is also an interesting question. We have a neural network with 2 hidden layers containing 2 neurons. The network contains 2 inputs and 1 output. Weights are 1, bias is 0, x is 10 and -1. We consider following 2 scenarios. We use max out activation for the hidden layers with k is equal to 2 linear function. Scenario 2, we use ReLU activation with dropout with a dropout probability of 0.5. And these are the options they have given. The outputs of both scenarios will be the same. Output of scenario 1 is expected to be greater than scenario 2 or vice versa. So how do we solve it? So see, we make it here only. So we have got 2 hidden layers, 1, 2, and this is some output layer, for example. Input is 10 and -1, bias is 0, and here they're having 2 neurons. So here weight will be 2 into 2 and all ones. So at this is A1, H1, A2, H2. Here what we will get, we will get 9 and 9. So in first case, what they have given, in first case, they are saying you take the max out activation. Max out activation, what it does in the max out, that if this is the neuron and you have got values, for example, 4, 1, 4. So in the next neuron, it takes only the maximum values, rest everything it makes 0. Is that clear?
So your voice is not audible.
Okay, okay. Now is it audible? Is it audible now?
Yes.
Okay. So this is the max out concept, that if you apply max out, for example, here you got 4, 2, 1, 3, 4. You applied max out on this. So it will take only the maximum values, in this case 4 and 4, rest everything it makes 0. So in this particular case, when you apply max, what will be your H1? H1 will be 9 and 9. Is that clear?
Yes, sir.
Here again W2 is 1, 1, 1, 1. So here again 18 and 18 will come. Okay, am I audible now? Clear now? Shall I commence?
Yes, sir.
Okay. Now see what will happen with the ReLU and with the dropout probability of 0.5. So in ReLU also you will get 9 and 9, and if you don't apply the dropout, then both 9 and 9 will go. But there is a dropout probability of 0.5. It means either of the neuron will get switched off, only one neuron will activate. So either in H1 will be 90 or 09. Is that clear?
Yes, sir.
This is the ReLU with dropout P is equal to 0.5. So now in this with again 1, 1, 1, 1. So this will become 9, and again it will 9, and again your dropout. So one of the neuron will participate. So here your output is what? 0, 9. So which output is higher? Output of scenario 1 is higher, expected to be greater than scenario 2. Is this clear? Any doubt? I can explain again. So we are going this.
So what is k equal to two linear functions in the previous question?
K is equal to linear function means that if the max out was like this, for example, this 5, 6, 7. So when you take the max out, you do it is like a stride.
Okay.
Okay. We move to next question. So consider a neural network with one hidden layer containing two neurons. Input layer contains two neurons. Output layer contains one neuron. ReLU is used for hidden layer. Sigmoid is used for output layer. Weight is 0.5. Bias is 0. Assuming a dropout probability of 0.5, if an input vector is 1 minus 2 is fed to network, which of the following seems to be the expected output? So this I will leave to your this. Please do this. You can find out the answer. Okay. So the same concept you have to use. Okay, so do this question again, you will get the answer. Or shall I solve it again? Anyone?
No, so we can do it on our own.
Okay, this is an easy one because I want to cover the CNN part more. So I will skip this is easy questions. Sigmoid function is used at all the hidden layers for what can be true. Initializing the weights to very high values causes the gradients to vanish. Again, we know sigmoid suffers from vanishing, and weight updates will be in the direction of first and third quadrant only. We have covered any problem in this question? Here they have given H2 basically 3, 2, 0, 1, 6, and they have given all the weights, if I'm not wrong, to 1. This yes, W's are ones. So here when you multiply this, here you will get 3, 2, 5, 6, 6, 12. And in this you are using softmax, so this will become 48 and 48. Your output will be 0.5 and 0.5. Here they have not given y, but we know that y can be either 1, 0 or 0, 1. So what do we do? Using this we update W4. So you check yourself, W4 can be updated. However, as soon as you go to this layer, you are using sigmoid of this, and here it becomes vanishing gradient, it becomes 0. So that's why all these updates are not updated. question is there. This we have seen. This vanishing gradient problem, wherever it is not vanishing gradient, we know sigmoid suffers. If 10H suffers, ReLU suffers, and ReLU 6 suffers. And rest everyone which is in the this leaky ReLU, GeLU, max out, they don't suffer from the vanishing gradient. Okay, I will leave this. This is a simple question. You can solve all that. I straight away, I think I will come to week 8. And week 8 also, I'll take one question and I will solve that completely for a
So
backdrop.
we'll be getting this PDF, right?
This PDF I might not be sharing it, so that I'm not allowed to share this.
Okay.
You can go through the recordings. So I will cover only one question on the backprop. Rest parameters I have solved it, and this I will take one question where there are two. They have asked F and K. Okay, this is the question. Can you see the question? This one is from your PIP only. Is question visible?
Yes, sir.
Okay. So question says, this is the input matrix X. There are two filters, K and F. You apply these two filters. You store in A. A will become something like one this, and this is a tensor. And I will cover it here only. I have gone through this question. So that's why I have chosen this question. And there is a bias also. So we go step by step. So in the question they have given, A is equal to X convolution by K and X convolution of F. This is the question. Then what do they do? I go to the next step. They flatten into C, flatten A, you get C. Then D, they have done max pooling with a stride of 2. And then next one, sum of the elements in D, store in D, sum the elements and pass through the ReLU activation for this. So I will select from here. So this is the forward prop which is there. So we can do the forward prop here only, and we have to update. Okay, finally, in the question they have asked sum of updated K and F and sum of updated biases. So let's go through the question. There is an input matrix. There are two filters. There is a bias with both filters 0.5. We obtain one tensor by doing convolution of X by K and X by F. Then we flatten this A into C. It means if I get the values like this, I write all the values here. So I'll get a C. C will be something like this, one dimension. On this we do max pooling by stride 2. So I take two elements, take the maximum and store in D. And finally E is the sum of D, and F is the Y output, Y hat or Y, which is the ReLU of E. And then we have to backprop and we have to update K and F, and we also have to update the biases, both biases, and we have to write this. So let's solve it and let's do step by step. So first we find A. So we do convolution by K. So here only 1, 1, minus 1, 1. So first will become 0.5. 0.5 from where it has come? From bias. Then we apply on this. Both are participating. This becomes 2.5. We apply here. Only one is participating, 1 and 1, 1.5. We come here. Both are participating, 1 and 1, 2.5. So this is with respect to K. I write A, K. Then we do with respect to F. So I apply on 1, 0, 1, 1, 1 minus 1, 0. So this becomes 0.5. I apply on 1, 0, 1, 1, 1, 1, 2.5. 1, 0, 0, 0, 1, 1.5. I apply here 1 minus 1, 0. So this becomes 0.5. So A we have got. No problem. This understood. Now for the second, C is flattening of this. So C will become, when I will flatten, it will become 0.5, 2.5, 1.5, 2.5, 0.5, 2.5, 1.5 and 0.5. Then we do D. D is a max out with a stride of 2. So here I get 2.5, here I get 2.5, here I get 2.5, and here I get 1.5. And y hat is equal to ReLU of sum of D is equal to ReLU of 2.5, 5 plus 4, 9. So your output is y hat is equal to 9. This forward pass understood? Anyone? Any doubt in this? Suraj? Hello.
Yes, sir.
Anyone? Any doubt in the forward pass? So I go back. Okay.
No, sir.
Okay. Very nice. So now we know these figures, and now what do? We take this figure and do the back prop now. So I will draw here. Okay. So see, we write down all these values. So here we have applied K, we have applied F. Here we got 0.5, 2.5, 1.5, 2.5. Here we got 0.5, 2.5, 1.5 and 0.5. When we came to C, it becomes 0.5, 2.5, 1.5, 2.5, 0.5, 2.5, 1.5 and 0.5. We gave it here sum, it became 9. Sorry, here we did D. So I got 2.5, 2.5, 2.5, 1.5. Here I did the sum. So here A1 I got 9. I applied ReLU on this, it became 9. So your y hat became 9. So this is your forward prop. Now for the back prop, for finding WL by WK and WL by WF. This is my output layer. So I want the loss here. And then I want the loss at these two places to calculate. So what do I need? I basically need WL by WK is equal to WL. Let's call this as A, B, this is C, this is D, and let's call this as E. WL by WK is del L by del E by del D by del C, and del C by del AK. K, this one, this is AK, and this is AL. Now in the question, let's see, this del L by del E will become del L by del Y hat, del Y hat by del E. In the question, they might have given us del L by del Y hat because they have not given the loss function. So let's check that. So yes, they have given del L Y hat is equal to 1. Okay, so this information is available in the question. So with this background, let's go.
Sir, in the chain rule, at the end, there must be del AK by del K.
See, del K, which is del AK by del K. Okay.
Yes.
Thank you so much. So del L by del Y hat, they have already given us 1. So we have reached here. Okay. Derivative of ReLU is what? It is 1. So we get 1 here. So here we have got del L by del E is equal to 1. Okay. Is this clear? Now, this sum which is there, in sum all the elements are participating. So your loss will also go through all elements. Am I right?
Yes, sir.
Okay, very nice. So see, del E by del D, due to this, it becomes 1. Okay, because all the neurons, they have participated. Here it is not that I make something 2.5 rest all 0, because it is a sum. That's why it is 1. Now when I go to del D by del C, here is the time where 2.5 came from here, this 2.5 came from here, this 2.5 came from here, and this 1.5 came from here.
Excuse me, sir.
Yes?
So del E by del D will be a vector or scalar?
Del D by what?
So del E by del D will be a vector, right?
Can you come again? You're hardly audible.
So del E by del D will be a vector or a scalar?
Del E by del D will be a vector. Okay?
Yes.
Okay. And now we come to del D by del C. So this 2.5 coming from here, this 2.5 coming from here, this 2.5 and this 1.5. It means all these neurons which are there, other neurons, they have not participated, they become 0. Is this clear? This concept?
Yes.
Okay. And now see, when you take to AK and you take del A by del C, this will become 0, this will become 0, this will become 1, and this will become 1. Is this clear?
Yes, sir.
And when you come here, this will become 0, this becomes 1, this becomes 1, and this becomes 0 when you take the derivative.
Right, sir.
Anybody, if you have got any confusion, you can ask me. Suraj, Puneet, Anand.
So why is it 1?
1, see, here it is 2.5, here
Yeah.
it is 2.5. So when I take del B by del C or del C by del B, this is del C by del A I have written. So del C by this point, this is also 2.5, this is also 2.5.
Okay.
So when you take derivative, it will become 1. Same value is there.
Okay. Okay. Yeah.
Okay, and rest all elements, they are not participating, it becomes 0.
Yeah.
See this process which I am explaining, it is basically to come here. Otherwise, when you see the derivative of this, like a question which was asked by just now, it is a vector. When you take derivative of del C by del D, it becomes a very, very big matrix. Okay, and when you multiply, finally you get this. So I'm just giving you the shortcut to arrive here. Okay.
Yeah.
Okay. So once we have reached here, now our life becomes easy. So our del L by del AK I have reached. Del L by del AF I have reached. I have got. So now my thing becomes del L by del K will be input convolution by this del L by del AK, which I have got. Okay, this I have got. So you do convolution on this, you will get here. So what are the values which you will get? Let's do convolution. 0 1 0 1, so only 1 is participating, you will get 1. You come here 0 1 1 1, only this part is participating, 1. 0 1 0 1, here you get 0. 0 1 1 1, you get 2. So you get 1 1 0 2. Del L by del F, you do.
Sir, I didn't get that.
Yes?
I didn't get that.
Your voice is slightly low. Can you speak slightly here, please?
Sir, I didn't get that. That convolution part.
Okay, so what you do, this is del L by del AK. You come here.
Yes, sir.
Okay. So for stride is equal to 1, so I'll write here. We have to find del L by del AK, which is equal to del L by del AK into del AK by del K. I can write this.
Yes, sir.
Now, if you see your AK is equal to X convolution by K.
Yes.
Del, and when stride is equal to 1, then del L by del AK will become X convolution by del L by del AK. Okay, this is valid when stride is equal to 1.
Okay.
Okay. So, and this will become del L by del AF. So you do the convolution of this. So when we do the convolution of this, let's find out what we'll get. 0 1 1, here 1 1, both are participating. This becomes 2. 0 1 1 0, only 0, here become 1. So this become 2 0 0 1. So using this, now I can update K and I can update F. This I can do. So we have reached here. Now interesting part is about I have to update the biases also. So there is a bias for K 0.5. There is a bias for F is equal to 0.5. And you see del L by del B is equal to del L by del AK by del AK by B. I can write this. And AK is equal to X convolution K plus B. We are adding the bias. So when I took the derivative of AK by del of B, it becomes 1. So what does it mean? That your del L by del B, remember this again, this will become sum of del L by del AK. and your del L, this for K, and del L by del BF will also become summation of del L by del AF. So this we can check what is the. So this I'm leaving to you. You complete this calculation part and you will get all your fundamentals clear about CNN backprop and how to update the parameters. And before we log off, I will quickly take another question which might be having different concept. So like here in this question, what is the concept which we have covered? There are two kernels which have been applied. We got on this, what we did, we flattened this kernel, then we applied a stride, and then we did the sum. So we got the y hat. When we came back, here is a ReLU. So we found the gradient of loss at the output layer. Then we passed it through the sum. We came from sum to here. All the neurons, they participated. But when we came to C, we saw only these are the neurons which are participating. When we came to AK and AB, only the neurons which were participating, we made 1, rest all we made 0. And that's how we got del L by del K and del L by del F. So can I leave this to you? In case you face any problem in this, you can post on Discourse. Otherwise, we have covered entirely full.
Sir, in this
can
question,
you please explain that? Yeah.
Yes, yes. Can you speak one by one, please?
Sir, can you scroll up to that question again? This question that you solved.
Yes.
Sir, in this, we have taken max, right? After C to D, we have taken max, right?
Max with a stride of 2.
Yeah. So why have we converted 2.5 to 1? Because in the earlier question that I had asked, you said that when we had ReLU, then the derivative of ReLU is 1, but for max, it would remain the same. Like 2.5 would remain the 2.5 only.
Okay. See, here, this part which is there. So I'll just cover it here. This is 1.5, 2.5, 1.5, 2.5. Okay.
Yes.
And this is your C which is there. Here 1.5, 2.5, 1.5, 2.5. For example, I'm taking for this only.
Yes.
Okay. Okay. When we came from here, we realized that only which one is participating? Only 2.5 and 2.5.
Yes, sir.
These two are not participating. So this straight away I make it is 0.
Yes, sir.
Now this is AK and this is C. When I'm taking the derivative, it is del C by del AK.
Yes, sir.
Now when you take the derivative, the value is same 2.5 and 2.5.
Yes, sir.
It is flying.
Yes, sir.
So when you take the derivative, it becomes 1 and 1. This also becomes 1 and this also becomes 1.
Sir, I understood this. So in the beginning that I had asked the question about this only, max and ReLU. Then in that case, then why didn't we convert it to 1?
See that your max which was there, it was here.
Okay.
It was at the output function. When you fly through the max, here you have got the output error, but here, for example, in this case, it would have been max. Then and for example, here it was 4. Then only this neuron would have participated. Rest everything you would have made 0.
Yes, sir.
Here it is a sum. So in sum, all the neurons are participating. So this loss will fly to all the neurons.
Okay, so the derivative in that case wouldn't be applicable. Like AK wouldn't be.
Okay, so I will take your question again. Your question was like this. This was this. We applied a filter and we got something. We applied ReLU on that. It was like this.
Yes,
and
sir.
then we got something. We applied max. And max value which is there. We applied, for example, sigma and we got y hat. It was like this.
Yes, sir.
Okay. So here, till here, we don't have any problem. We can come
Yes,
here. A, B, C. We can come here. So this is delta C. We have come. Now here, when you see in your from forward prop, you find out which value is your participating. So in case this is a 4 which has participated, your rest everything will become 0.
Yes, sir.
Okay, and this is 4. And in ReLU also, if you remember, I had made this 4 as 1 because when we take the derivative, it becomes 1.
Yes, sir.
Okay, and you see in this question also, when you're taking derivative, these are becoming 1, 1.
Yes, sir.
Okay,
So in the like you scroll down.
yeah, this one,
Here instead of ReLU, if
yeah,
we had done max here,
okay, okay. So if you take the max, okay, then this layer goes off.
yes, sir.
So if you take max, this max will go straight away here.
Yes, sir. So let's say if this was 1, 2, 3, 4,
Okay, okay,
and
okay, okay. I've understood your question. Confusion. So this is 1, 2, 3, 4. 4 comes here,
yes, sir.
and then you directly feed into this. Now this will become 0, this will become 0, this will become 0, this will remain 4 because there is no derivative.
Okay, okay, because this is the first layer essentially.
First layer, yes.
Okay, okay, got it, sir.
Okay, and whatever the loss is flying, for example, you have got loss, for example, 0.002 here. That loss will get multiplied with this.
Yes, sir. That.
Okay.
Yeah.
Okay, so this calculation I will leave to you. So this is the most complex question, or I will not call complex, most lengthy question which has been asked in the PYPs. That's why I wanted to solve it. And quickly, I will.
Would you just once explain the del E by del D trick that you applied?
Del
Instead
E
of
by-
vector, you write just del E by del D.
Del
Instead of vector of ones, you just wrote a scalar one. So what was the reason?
I have not written, okay, where I have written a scalar. Del E by del D is your 2.50. This is a 2.5, that, no?
Yes.
Where have I
2.5 to 2.5.
Where have I written scalar? Scalar will come
Actually,
here.
del E by del D will be a vector, right?
Yes, this will be a vector. Here, for this particular function, which y hat we are using for ReLU, del L by del E will be a scalar. Is that okay?
Yes, sir, right.
Okay, and from here when we come, it will become a vector. And now when you take a vector, a derivative of a vector, it becomes a matrix.
Yes, sir, Jacobian matrix.
Okay, and when you do this, finally, that's why I was omitting this part, okay, for simplicity purpose. Finally, when you multiply, you get this only.
Okay.
Okay.
Okay, sir.
I will just try to remove that complexity from the question, otherwise it becomes long. And finally, you get this only. I'm giving you a quick part, okay, for the quiz purpose. Okay.
Okay, sir. Got it.
Okay. Now let's take another example before we log off. It has become slightly late. Okay. Okay, I think this was one more detailed example. So I'll request, okay, everyone to finally you solve these questions. In case you face any difficulty, please post it on Discord. I'll reply to that. And any doubt till now before we log off? Anyone?
So can we just get the PDF of questions, if not the solutions?
See, PDF of the questions, they are available here. So many resources are there with all of us. You can post on the WhatsApp group. Okay, I will share the link with you. Okay, Nitish?
Not PYQ, sir. This PDF. Can we get this?
This PDF. See, I'll tell you the reason, okay, why I'm not sharing. See, many times when we do the calculations, I might have committed some human errors. I might have written somewhere. Now, when I share it with, okay, I'm also a fellow student like you. When I share, it becomes a template. Now, everybody will think this is the correct step. So that's why I don't want to share. That is precisely the reason.
Okay, sir.
Okay. Chalo, let's call it off. Okay. Thanks for your time. Thanks for your patience. All the very best. Okay.
Thank you so
Thank
much,
you so
sir.
much, sir.
Thanks for taking out the time.
Yeah. Thank you. Have a nice day.
Thanks, sir.
Bye bye.